Welcome back to the deep dive. We've all been there, right? You're reading a white paper, or maybe you're just scrolling through a tech blog,
hmm
and the writer starts throwing around terms like hyperparameter tuning, vanishing gradients, or internal covariate shift.
All the buzzwords.
Exactly. And you nod along, maybe you even, use these words in meetings. But if someone actually pressed you, if they said, okay, but physically, mathematically, what is happening inside that machine,
Yeah.
you might freeze up a little.
It's the classic black box syndrome.
Hmm.
We all know that it works because we see the results in things like ChatGPT or Midjourney, but the how
Mm-hmm.
that often gets hand-waved away is just, advanced algorithms.
Right. And I think a lot of us have this lingering imposter syndrome where we treat deep learning like it's some kind of magic. So today's mission is to dispel that. We're going to ignore the hype and look strictly at the engineering.
These are the weeds.
We're going to tear down the engine and look at the actual mechanics, the activation functions, the normalization, the gradient descent, the actual math that makes the thing learn.
Which is a great approach, because when you strip away all the sci-fi talk, deep learning is really just calculus and linear algebra, but at a massive scale. It's not magic at all, it's just optimization.
So let's set the stage. We have AI, machine learning, and deep learning. We know they're not synonyms, but I feel like that distinction gets muddy, especially between ML and deep learning. Where's the hard line?
Think of it like a set of Russian dolls. Artificial intelligence is the biggest doll. It's any technique that lets computers mimic human behavior.
Okay.
Machine learning, or ML, is the next doll inside. ML is specifically about using statistical methods to let machines improve with experience. But deep learning, that's the smallest doll, a subset of ML with a very specific structural requirement.
It's a neural network.
Correct. While traditional ML, like a random forest or a support vector machine, might use all sorts of statistical tricks, deep learning is exclusively built on artificial neural networks.
Yeah.
These architectures are, loosely inspired by the biological brain. You have layers of neurons connected by weights.
And this is where the history gets a little weird, because the math for neural networks isn't new, right? I mean, the perceptron, the basic unit, that's been around since the late 50s.
Right. And backpropagation was popularized in the 80s.
So why are we only seeing this huge explosion now, post-2012? Why didn't we have GPT-4 running on Windows 95?
It wasn't a lack of ideas. It was a lack of resources. If you look at the timeline, there wasn't one big bang moment. It was more of a convergence of 5 distinct factors that all came together around 2012. The first, and maybe the most obvious, was data.
The fuel.
Exactly, the fuel. Deep learning is incredibly inefficient with data compared to us. A child sees one cat and knows what a cat is for life. A neural net needs, 100,000 labeled images of cats?
A massive amount.
The internet boom, and especially the smartphone revolution post-2010, finally gave us that digitized labeled data set we needed, what we now call big data.
But you also need an engine to burn that fuel, and this is my favorite part of the story because it involves this accidental hero, NVIDIA.
It is a funny historical accident, isn't it? NVIDIA wasn't trying to solve artificial general intelligence. They were just trying to make Call of Duty look photorealistic. They built GPU's graphics processing units specifically for gaming.
And the connection there is matrix multiplication.
Precisely. Think about a 4K monitor. That's over 8 million pixels. To render some 3D explosion, the computer has to calculate the color and intensity of every single one of those pixels at the same time, 60 times a second.
Which requires massive parallel processing.
And it just so happens a neural network is mathematically the exact same problem. It's millions of neurons like pixels that all need to be updated simultaneously.
So the AI researchers basically just hijacked gaming hardware.
They did. They
Yeah.
realized they could repurpose these graphics cards to train their networks hundreds of times faster than a standard CPU ever could. And that unlocked the speed. Then you had the frameworks, TensorFlow, PyTorch, which made the coding easier. You had pre-built architectures like ResNet or YOLO, so you weren't starting from scratch. And finally, you had the community, which just exploded, sharing everything open source.
So the infrastructure finally caught up with the theory. Now let's get into the actual soul of the machine. The outline mentions representation learning, and I think this is the key difference between traditional ML and deep learning. Can we use the resume classifier example?
Sure. Let's say you want to build a system to predict if a software engineer gets hired, just based on their resume. In traditional machine learning, you have a massive bottleneck. The human.
You're talking about feature engineering.
Right. You, the engineer, have to sit down and literally decide what matters. You create a column for years of experience, a column for GPA, maybe a column for knows Python. You are manually extracting the features.
And if you forget to add a column for, say, open source contributions, the model can't see it.
It's invisible to the model. The model is only as smart as the human who defined those columns. Deep learning just flips this on its head. You don't create columns. You just feed in the raw text of the resume. The network then performs what we call representation learning. It figures out the important features all by itself.
But how does it know that Python is a coding language and not, a snake?
That's where it gets really fascinating. Through training, the network learns what are called embeddings. It maps words into this high-dimensional vector space. So it figures out that the mathematical vector for Python points in a similar direction to the vector for Django or Java, and that those are very far away from the vector for management.
So it's learning semantic relationships you never explicitly taught it.
It is. It's not just counting keywords. It's understanding context. The early layers of the network might just recognize letters or simple words. But as you go deeper, the layers start combining those simple features into more complex concepts. Layer 4 might recognize tech stack. Layer 10 might recognize seniority level.
Which sounds amazing, but there's a catch in there. We're trading control for performance.
That's the black box trade-off. In the manual ML version, if the model rejects a candidate, I can look at the decision tree and see, oh, it's because their GPA was weighted heavily and it was too low.
You can explain it.
You can. In deep learning, that decision is distributed across maybe a billion floating point numbers. We can't always point to one specific reason why that resume was rejected.
Which is an engineering nightmare if you need to debug it. But let's go deeper into the mechanics. We have these layers, we have neurons, but a neuron is just a container for a number. What makes it actually fire? We have to talk about activation functions.
This is the spark plug. A neuron takes inputs, multiplies them by weights, adds a bias, and then it has to decide what to output. That decision, that's the activation function.
And the sources are really emphatic about this. If you don't use a nonlinear activation function, the whole network is basically useless. Why is that? If I stack 100 layers of linear neurons, isn't that still a deep network?
It's deep, sure, but it's dumb. It's what we call the linear trap. Mathematically, a linear function of a linear function is just another linear function.
Okay.
You could collapse those 100 layers into a single layer and get the exact same result. You gain zero complexity.
So you're just drawing a straight line through data that is clearly curved.
Exactly. Real-world data is messy. It's nonlinear. To capture that, you have to be able to bend the line. And that's what an activation function does. It introduces nonlinearity.
So let's look at the evolution here. We started with sigmoid.
The old standard. It's that classic S-curve that squashes any number down to a value between 0 and 1.
Which is great for probabilities.
Great for probabilities in the output layer. But it's terrible for deep networks because of something called the vanishing gradient problem.
This is where the training signal just dies out.
It just fizzles out. When you train a network, you're sending error signals backward. That's backpropagation. The problem with sigmoid is that at the far ends of that S-curve, the slope is almost completely flat.
So the gradient is close to 0.
Near 0. So as you multiply these tiny, tiny gradients back through the layers, the signal just dissolves into nothing. The early layers never get the message that they need to update their weights. They just stop learning.
So then the industry shifted to ReLU rectified linear unit. And on the surface, this thing looks almost too stupid to work. The formula is just max 0x.
I know, it feels like a trick.
If it's positive, you keep it. If it's negative, you make it 0. That's it.
It looks simple, but the implications are profound. First, it solves the vanishing gradient problem, because for any positive number, the slope is always 1. The signal doesn't degrade. But the real magic, and this is often overlooked, is that ReLU induces sparsity.
Sparsity. So it's actively turning neurons off.
Yes. In a sigmoid network, almost every neuron is firing a little bit, all the time. It's very noisy. ReLU forces any negative input to be exactly 0. This means at any given moment, a huge portion of your network is completely inactive.
It's like Marie Kondoing the network. It's quieting down the noise so the important signals can stand out.
That's a great way to put it. It makes the representation much more efficient. If you're looking at a picture of a cat, the neurons responsible for truck wheels should be at 0. They shouldn't be at 0.001. They should just be off. ReLU enforces that discipline.
Okay, so we've got efficient firing. Now let's talk about the terrain. We have a loss function, which is basically a score of how wrong our model is, and we want to get that score as low as possible. The sources talk about data scaling and batch normalization as ways to smooth out that path.
Right. So imagine the loss landscape is a physical terrain, like a mountain range. We want to get to the lowest valley. If your data isn't scaled, so you have a feature like age from 0 to 100 and another like salary from 0 to 100,000, the landscape gets warped.
Okay.
It becomes this long, narrow, elongated canyon.
And if you're trying to walk down a narrow canyon?
You spend all your time bouncing off the walls. The optimization algorithm zigzags wildly back and forth and takes forever to reach the bottom. So what we do is we scale the inputs. We force everything into a standard distribution, a mean of 0, standard deviation of 1. Now the canyon becomes a nice symmetrical bowl. You can walk straight down.
That makes perfect sense for the raw data coming into the first layer, but one of the sources brought up internal covariate shift, this idea that the deeper layers also face this problem.
This is the moving target problem. As the network trains, the weights in layer 1 are constantly changing. That means the distribution of the outputs from layer 1, which are the inputs for layer 2, is also constantly changing. So layer 2 is trying to learn, but it's constantly having to readapt to what layer 1 is doing. It's like trying to learn to dance while the floor keeps tilting at random angles.
So batch normalization is just applying that same scaling, but inside the hidden layers.
Yes, but with a brilliant twist. It forces the layer's output to be standard mean 0, standard deviation 1. But then the designers realized, wait a second, what if the network actually needs the data to be shifted? What if a mean of 0 is actually bad for learning this specific feature?
So they gave it an escape hatch.
Exactly. Batch norm has 2 learnable parameters, gamma for scaling and beta for shifting.
Yeah.
It's like saying to the network, look, I'm going to standardize this data to keep your training stable, but T, I'm also giving you these 2 knobs. If you decide you need to stretch or shift the data back to learn effectively, you can turn the knobs yourself.
I love that. It's like a safety net, but you give the acrobat a pair of scissors just in case.
And it works. It allows for much higher learning rates. It drastically speeds up training. It's an absolute staple in modern deep learning.
Okay, so we have the structure, the activation, the normalization. Now we need to actually move. We need to update the weights. This brings us to gradient descent.
The navigation system.
The sources outline 3 ways to do this: batch, stochastic, and mini batch. Can you walk us through the trade-offs?
Sure. So batch gradient descent is the cautious perfectionist. You look at every single data point in your data set, all 1 million images, calculate the average error, and then take one single step down the mountain.
That sounds excruciatingly slow.
It is. It's computationally heavy and needs a ton of memory. But the step you take is very accurate. You are definitely moving in the right direction.
Then you have the complete opposite, stochastic gradient descent, or SGD.
The drunk walk. You just pick one random image, calculate the error for that single point, and take a step. Then you pick another random image, take another step. The path is incredibly jagged, noisy, and it zigzags all over the place.
But the sources say that this drunkenness is actually a feature, not a bug. Why would noise be a good thing?
This gets us to a concept that's even trickier than local minima. It's called saddle points.
Saddle points.
Yeah, imagine you're standing on a horse saddle. If you look front to back, the terrain goes up. But if you look side to side, it goes down. You're at a point where the slope is flat, but you aren't at the bottom. In high-dimensional spaces, and we're talking millions of dimensions, these saddle points are much more common than local minima.
And the cautious perfectionist batch gradient descent gets stuck there.
It does, because the gradient is 0. It's flat batch gradient descent just stops, it thinks it's done.
Yeah.
But SGD, because it's so noisy, because it's drunk, that randomness creates enough jitter to kick the model off the saddle and force it to keep rolling down towards the true minimum.
So the instability actually helps it escape these tracks.
Exactly. But of course, purely random is too unstable for its own good. So we compromise with mini-batch gradient descent. We take small batches, say 32, 64, 128 images.
And these are always powers of 2, I notice.
That's purely a hardware optimization. GPUs just love powers of 2 for memory alignment. So mini-batch gives you enough stability to make steady progress, but enough noise to escape those saddle points. It's the industry standard for a reason.
So let's synthesize all this. When we say a machine is deep learning, we're not talking about magic. We're saying we've taken a massive data set, we've fed it into a neural network, we use ReLU to shut off irrelevant neurons and create sparsity. We use batch norm to keep the internal signal stable while still giving the network flexibility. And then we use mini-batch gradient descent to navigate this ridiculously complex landscape using just enough noise to avoid getting stuck.
That is the recipe. It's a series of very clever mathematical solutions to very specific optimization problems.
It really changes how you look at the output. When ChatGPT writes a poem, it's not being creative in a human sense. It's the result of a massive optimization equation finding a local minimum in a billion-dimensional space.
It is. And that leads to the final point we need to consider. We have built these unbelievably powerful engines. They're beating humans at medical diagnosis, at strategy games, at generating creative art. But because of this black box nature, because the logic is spread across millions of weights, we have traded interpretability for performance.
We know that it works, but we can't always prove why it made a specific choice.
Right. And if a lone algorithm denies an application, and you ask why, the honest answer is because the gradient descent algorithm found that this particular combination of 50 million weights minimized the error on the training set. And that's not a satisfying answer for the person who's denied the loan.
Or for a regulator.
Exactly. As engineers, we're getting better and better at building the engine, but we're still figuring out how to build the dashboard.
That is the challenge for the next decade. Well, thank you for popping the hood with us today.
My pleasure. It was fun.
And for everyone listening, next time you hear deep learning, don't just gloss over it. Think about the sparsity, the gradients, and the math making it all tick. There's a lot of beauty in the engineering. Thanks for diving deep with us. We'll see you next time.